Okay, in this video we're going to talk about limits. We're going to be able to find the limits of functions both graphically and numerically, use the properties of limits to evaluate the limit of some functions. We'll use analytic techniques to evaluate functions to simplify that evaluation. We'll talk about one-sided limits and unbounded behavior of some functions. But what is a limit? The limit of a function. In everyday language, people refer to a speed limit, or a wrestler's weight limit, or the limit of one's endurance, or stretching a spring to its limits. These phrases all suggest that a limit is a bound, which on some occasions may not be reached, but on other occasions it may be reached or exceeded. Consider a spring that will break only if a weight of 10 pounds or more is attached. To determine how far the string will stretch before breaking, you could attach increasingly heavier weights and measure the spring's length S for each weight W, as shown in the figure. So here in the figure at 0, the spring is fully compressed. We put a 3-pound weight on it, it stretches out a little. 7.5-pound weight, it stretched out more. 9.5, it stretched out even more. A 9.999-pound weight stretches us out even more. The stretched out length of the spring is S. And remember, if we put a 10-pound weight on, that spring is going to break. So if the spring length approaches a value of L, then it's said that the, quote, the limit of S, or how long S will stretch out to be, the limit of S as W approaches 10. So remember, W, the weight is approaching 10. If we put a 10-pound weight on, the spring will break, but we can get closer and closer to 10 pounds by 9.5, 9.999, and so forth. So if the spring length approaches a value of L, then it says the limit of S as W approaches 10 is L. L is the limit. A mathematical limit is much like the limit of a spring, and the notation for this limit is right here. And how do we read that in English? The limit of f of x as x approaches c is L. Another way I've commonly heard this referred to is the limit as x approaches c of the function f of x is equal to L. In example 2, we're going to find some limits both numerically and graphically. Numerically first. So they're asking us here to find the limit of, or find the limit as x approaches 1 of our function f of x. And our function f of x is this quotient, x squared minus 1 divided by x minus 1. What happens if we plug our x value right in there? What happens if we plug in that x is 1 right off the bat? Well, we'd get 1 squared minus 1 divided by 1 minus 1. And you can see right there we're going to run into trouble because our denominator is 1 minus 1, and that's a 0, and we cannot divide by 0. The world will blow up. And our numerator also, 1 squared minus 1 is also 0. This is a special case. 0 divided by 0 is called indeterminate form. And that tells us we're not going to be able to find the limit by just plugging that x value of 1 in. So what we're going to do is get real close to plugging 1 in without actually plugging 1 in. And our TI-89s are going to help us make this a little easier. So we're going to go to the Y editor, Green Diamond F1. And we're going to plug in our function. Make sure to parenthesize off the numerator and denominator, so when you hit enter it should look like this in your display. And then go to the table set, Green Diamond F4, make sure the one setting is set to ask and not automatic. And then we're going to go to the table, Green Diamond F5, we're going to plug in these x values and see what y values pop out. So again, we can't plug 1 right into the function, but let's plug in some numbers close to 1. If we start out with 0.9, if we go to our table and plug in a 0.9 into the function, you know we're not plugging in a 1, so we will not get a divide by 0, and our function output is 1.9. And you know 0.9 is close to 1, but we can get even closer. Let's put in 0.99, even closer. And if we plug that in, we'll see on our display, we'll get out a 1.99. And let's get even closer. Closer than 0.99 is 0.999. And if we plug that into the function or the calculator, we get out an output of 1.999. You know, our x values are getting closer and closer to 1, and it looks like our y values are getting closer and closer to 2. Now, that was from the left side of 1, or numbers less than 1. Let's see what happens when we plug in numbers greater than 1 on the plus side of 1. So if we go to our table and plug in 1.1, we get an output of 2.1. Let's get closer. 1.01. That's closer than 1.1, and our table gives us an output of 2.01. And if we get even closer, 1.001, we get an output of 2.001. Now look at our y values, 2.1, 2.01, 2.001. As we get closer to 1, our y values are getting closer to 2. So what happens? It looks like if we could plug 1 into the function, remember if we plug 1 in, we get our divide by 0, and we can't have that. But if we could, it looks like we'd get an output of 2. That is our limit. The limit of this function as we approach that bad number 1 looks like we're getting closer and closer to an output of 2. So that's numerically. We can use our calculator and plot some points and figure out numerically what's happening with this limit as we approach that number 1. Let's take a look at this graphically. So our function was x squared minus 1 over x minus 1. What happens if we plug 0 in? Let me switch to red here. If we plug in an x value of 0, we're going to get minus 1 over minus 1, which is 1. Here's the number 1 that we're interested in. We plugged in 0, we got an output of 1. What happens if we plug in 2? 2 squared minus 1 is 4 minus 1, or 3. And 2 minus 1 in the denominator is 1. So here we would have an output, a y output of 3. And then we can use our table. As we go over to 0.9, pretty close here to 1, our output is just under 2. And we plug in 0.99, and we get even closer to 2. And plug in 0.999, we get even closer. So from the left here, it looks like we're approaching a y output of 2 as we get closer and closer to 1 on the y-axis. If we go a little bit above it, if we plugged in our 1.1, we got an output value of 2.1, or a little bit above the line. And we plugged in numbers closer and closer to our x value of 1, and we got closer and closer to a y value of 2. But we know this graph right at this point, if we do plug in 1, it's undefined. There's a hole in the graph right here. But as we approach it, and let me switch to black here, as we approach x values of 1 from numbers just a little bit less to it, we're getting closer and closer to that hole on this line. And when we went above 1 from 2 and we started getting closer and closer to 1 from above, we were sliding down this line and we were getting closer and closer to that hole without actually falling in it. So here on the x-axis, as we approached 1 from either side, above and below, we were approaching 2 from above and below on the y-axis, or we were getting closer and closer to this hole without touching it. So here our function x squared minus 1 divided by x minus 1 looks like a straight line. But on that straight line, we have a hole at an x value of 1. And the height of that hole on our y-axis is 2. And here's the book or the picture that came with the book. Here's our function, x squared minus 1 divided by x minus 1. We were looking at the limit as we approached 1. What happened as we approached 1 on the x-axis from either side? Well, we were approaching the hole in the graph right above x equals 1. And the height of that hole on the y-axis was 2. Here's a slightly different one. Now it's a little different because our function has absolute value bars. Find the limits graphically and numerically. The limit again as we approach 1 of this function. The absolute value of x minus 1 divided by x minus 1. And we're going to again approach from above and below. So we go to our graphing calculator and we want to plug in this function. We're going to the y editor. To get the absolute value bars, you want to hit the catalog key. Catalog. And one of the first things you'll see, it's all listed alphabetically, is ABS. and they give you a left parenthesis. ABS left parenthesis. That stands for absolute value. So now you want to type in x minus 1, close parenthesis. There's your absolute value of the quantity x minus 1. And then hit the divide by key and parenthesize off the denominator x minus 1 and hit enter. In your display, your function should look like this, absolute value bars included. And once we have our function put into the y-editor, we're going to go to the table, green diamond F5, and plug in our x values just like we did in example 1. So if we plug in 0.9, and we could even do this without the calculator, we'd have absolute value of 0.9 minus 1 divided by 0.9 minus 1. Our numerator would be negative 0.1 absolute value bars divided by 0.1 not an absolute value bars. So we're going to get 0.1 divided by 0.1, which is, well, our denominator, yes, would be negative. 0.9 minus 1 would be negative. Denominator would be negative. And if you do punch it in the calculator, you are going to see an output of negative 1. And you get even closer to 1. Because remember, at 1, boom, the world blows up. So 0.9 was close. We're getting even closer to 1, 0.99. And we see our calculator gives us an output of the same, negative 1. Plug in 0.999, and we get the same output, negative 1. So as we approach here from the left side, from numbers less than 1, our limit looks like it's approaching negative 1. Now let's hop on the other side of numbers greater than 1. So we'd have 1.1 minus 1 in absolute value bars divided by 1.1 minus 1, and we'll see an output of 1.0. And get closer to 1, 1.01, same output of 1. 1.001, we're getting closer and closer to the hole in the graph at the x value of 1, and we have an output again on the y-axis of 1. So as we approach from the left side, we're approaching negative 1. And as we approach from the right side, we're approaching positive 1. Two different limits. So we found it numerically. We're coming to one number from the left and a different number from the right. Let's check it out graphically. Let's see here. Our function again was absolute value of x minus 1 over x minus 1. And let's say here on our y-axis, I'll use red on the left. If we plug in negative 1, 2, 3, 4, here's negative 4. Oops. If we plug in a negative 4, we're going to get negative 4 minus 1 in absolute value bars divided by negative 4 minus 1, or 5 divided by negative 5. And that is going to be an output value of negative 1. If we plug in x is negative 3, it'll be 4 over negative 4, which is, again, negative 1. And if we plug in negative 2 for our x value, we'll get the same negative 1, the same negative 1. And as we get closer and closer, to our what do we call this? Our little arrow number. Remember, we were looking at the limit as x approaches 1. You know, here's x approaches 1, so we know at that point we're going to have a hole in the graph somewhere above or below. And as we plug in, well, we'll plug in 0. 0 minus 1 is negative 1. The absolute value bars make it positive. Divided by negative 1 is still negative 1. And here's our, again, our a number of interest, our arrow number. As we get closer and closer to it, our limit from the table looked like it was going to be at negative 1. So here's our line. We're approaching from the left. We're getting closer and closer to our x value of 1, and it looks like we're approaching a hole in the graph at negative 1. So let's hop onto the other side of the our arrow number, let's call it, x is 1. When we were on the other side in our table, when we were over here on numbers greater than 1, you know, like over here, I'll switch to blue, 1, 2, 3, 4. Here's x is 4. If we plug 4 into the function, we're going to get 4 minus 1, and the absolute value bars still make it positive, over 4 minus 1, and that's 3 divided by 3 is positive 1. And if we plug in 3, we get 2 over 2, or 1. As we plug in numbers getting closer and closer to this x value of 1, we stay right here on this horizontal line. And our table showed us that as we're approaching 1 from numbers above, we're always at a y value of 1. And we know there's a hole in the graph at 1. So here again, as we're approaching from numbers greater than 1, we're sliding down this line. And at x is 1, our table told us it looked like we had a hole in the graph at a height of 1 on the y-axis. So it's sort of like there's two holes in the graph. We have one below us at x is 1 at a height of -1, and we have one above us at a height of +1 on the y-axis. So just like our table here, on the left, as we approach from numbers underneath, we are approaching a hole at -1. As we are approaching from above the value of 1, we are approaching a hole at +1. And this is the graph of that situation. Again, when we plug in 1, we get a 0 divided by 0 scenario, indeterminate form. So the function is not defined anywhere above that x value. We have holes in the graph. And here's the picture that came with the book. So here's our x value of 1. That's our number of curiosity, our arrow number, so to speak, as x approaches it from either side. And this limit, we're going to say that it does not exist. As we approach from one side, we had a value here at -1. As we approach from the other side, we had a value up here at +1. Because we were approaching two different numbers, the total limit, the overall limit, does not exist. Now, are all of these that tricky? Do we always have holes in graphs? No, not at all. Find the limit of this function. The limit as x approaches 1 of x squared plus 1. So, let's see here. If we plug that into our table, as we approach from above and below, it looks like we're getting closer and closer to the number of 2. And this is a nice easy one. We should always try first. Let's plug that number straight into the function. As x approaches 1 of this function. Well, if I just plug that 1 straight in, here's x squared plus 1. If I plug my x value of 1 in, I get 1 squared plus 1. And 1 squared plus 1 is 2. In these other examples, we had a divide by 0 scenario when we plugged in that number that we were approaching. Here, as we approached 1, we had 0 divided by 0. Here, as we approached 1, 0 divided by 0. In this example, we don't have to worry about that. There is no chance to divide by 0. We just plug that number 1 in, we get our limit of 2. As we look at the graph of that, there's no hole in the graph at all. X squared plus 1 is just a nice parabola opening upward. As we approach, let me make this just a little bit bigger. There we go. As we approach the number 1 on the x-axis, here they were asking us the limit as x approaches 1. So as we approached 1 from below, our y values were sliding up this parabola. They were approaching 2 from below. As we approach that number 1 from above, numbers greater than 1, we are sort of sliding down the parabola here toward this point, or sliding down the y-axis to this point at 2. As we converged on 1 on the x-axis, we converged on 2 on the y-axis, and that was our point. There was no hole in the graph, so that limit is just 2. So there's 3 important ideas to take from these 2 examples. Saying that the limit of the function approaches some number L, as x approaches some number on the x-axis, in our examples it was 1, means that the value of the function, f of x, that's a value on the y-axis, may be arbitrarily close to our number L by choosing x values closer and closer to c. And that's what we did on our tables. As we got closer and closer to our number of interest at the middle of the table, we were getting arbitrarily close to some number on the y-axis. Idea number 2. For the limit to exist, you must allow x to approach c from either side of c, from above and below. If the function approaches a different number as x approaches c from the left than it does as x approaches c from the right, then the limit does not exist. And that was example 2b with the absolute value. As we approached from either side, we were approaching different numbers. As we approached from the left, we were approaching -1. As we approached from the right, we were approaching +1. The limit was different from either side. Here was our number at the middle of the table. We were interested in 1. As we approached from either side, we came to 2 different numbers. So that limit does not exist. And the third idea, the value of the function f of x when x is c does not have a bearing on the existence or non-existence of the limit as x approaches c. For instance, in example 2a, the limit f of x approaches 1 even though the function was not defined. That's where we add a hole in the graph. Here was our hole in the graph. Just because we don't have an output value, if we plug 1 in, there's a hole in the graph, we don't get the output value of 2. Just because the function's not defined there at that point doesn't mean that the limit doesn't exist. As we approached from either side, it sure looked like we were approaching 2. That was our limit. Even though the function is not defined, the limit still exists. And here's our formal definition of a limit in the box here. If f of x comes arbitrarily close to some number L, that's just a number on the y-axis, as x approaches c from either side, then the limit of f of x as x approaches c is equal to that number L. And we read this as the limit of f of x as x approaches c is L. So limits have some properties. Many times the limit of f of x as x approaches c is simply that number f of c, as shown in example 1. Whenever the limit of f of x as x approaches c is, and here we have the limit of f of x as x approaches c, we just take that c and plug it in, f of c. This limit can be evaluated by direct substitution. Just whatever your little arrow number is here, just take that number and plug it in and see if it works. Sometimes it will. In the next section, you'll learn that a function that has this property is continuous at the point c. It's important that you learn to recognize the types of functions that have this property. Some basic ones are given in the following list. So here are some properties of limits. Let b and c be some real numbers, and let n be a positive integer. So the limit as x approaches c of just some number b is equal to b. That's kind of confusing. The more we'll talk about that, or we might be able to clear it up with a quick sketch here. So here, let's just graph a quick horizontal line. Let's say this is a height of 2. So here's our function. We could write that as y equals 2. That's just a horizontal line. Or in function notation, f of x equals 2. No matter what x value we plug in, we could plug in this x value of 3, and we'd go up to the function, and that's at a height of 2. We could plug in this value of 6. F of 6 is just going to equal 2. No matter what we plug in, we're going to get an output somewhere on this horizontal line at 2. So the limit of f of x is equal to 2. We could write the limit as x approaches 7 of 2 is equal to what? The limit as x approaches c of b is equal to b, that's kind of abstract and vague, but no matter, this might be easier to see with some concrete numbers in there. Our function is y equals 2. That's just this horizontal line. No matter what number I put down here to approach from either side, I could put it over here at negative 2. The limit as x approaches negative 2 is still going to equal this number. As we approach negative 2 from either side, on our function, we're going to be approaching this point at a height of 2. So no matter what the arrow number is here, no matter what that c is, if it's just a number here, that's what we're going to approach. Number 2. The limit of x as x approaches c is just c. We plug that c value in for the variable. Here, b was a concrete number. Now, x is a variable. As we approach some value c, we can just try plugging that value c in, and there it is. That's our limit. It works for exponentials. We have some function, x to the n power. As we plug in numbers for x, as we approach this number c, we just plug that c in for the x value, we get c to the n power. And it also works with radicals. We have our nth root of x. Well, as we approach the value of c, we can just plug that c right in for x, and that limit is going to be the nth root of c. In property 4, if n is even, then c must be positive. If our index is even square roots or fourth roots or sixth roots, we got to have a positive number underneath that radical. Okay, and by combining the properties of limits with the rules for operating with limits shown below, we can find limits for a wide variety of algebraic functions. So let b and c be real numbers. B and c are just, any number you want. Whole numbers, pi, or square roots, whatever you want. They're real numbers. N is some integer. And let f and g be functions with the following limits. The limit of f of x is equal to some number L. And the limit of g of x is equal to some number k. And these are the limits as we both approach the same input value, c. So we're approaching c here. F of x has an output value of L. We're approaching the same c value here. This other function, g of x, has this other limit, k. So our first operation is the scalar multiple. We could have the limit as x approaches c of b times f of x. And remember, b is just some number. I like to think about it this way. We can take that b and factor it out front. So now we have b times this limit of f of x. And we know the limit of f of x here is equal to L. So now we have b times that limit L, or just b times L. Let's see here. Number 2, sum or differences. If I have the limit as x approaches c of these two functions, either added or subtracted, doesn't matter. I can take the limit of the first one, f of x, and get its value L, and then add or subtract, whatever the case may be, the limit of the g of x function, which is k. So the limit of the sum, or the limit of the functions is equal to the sum or difference of those functions. The limit of that is equal to just the sum or difference of their limits. In number 3, we have a product operation. We have the limit as we approach c of f of x times g of x. Well, we know the limit of f of x is L, the limit of g of x is k, so our limit of the product is the product of the limits, L times k. We have a quotient property or operation. We have our limit as we approach c of, now it's a function divided by the other. It's f of x over g of x. Well, the limit of f of x is L, the limit of g of x is k, so the limit is just L divided by k, as long as k does not equal 0, because we don't want the world to end. We also have the power operation. The limit as x approaches c of our function f of x, all raised to the nth power. Well, the limit of f of x is L, whatever L is, and then now it's just L to the nth power. And it also works for radicals. We know the limit as x approaches c of f of x is equal to L. So since it's under a radical sign for the nth root, it's just the nth root of L. A lot of this is just sort of like our direct substitutions. In property 6, if n is even, again, if that index is an even number, our L has to be positive. So here in example 3, it's telling us to find the limit as x approaches 2 of x squared plus 2x minus 3. And I think what they wanted us to do in the book here is we have the limit of 3 things added together. So it is the limit as x approaches 2 of the first piece, x squared, plus the limit as x approaches 2 of this piece of the function, 2x, and then minus the limit as x approaches 2 of 3. So here's our minus and here's our plus. And now we could just evaluate this piece by piece. We plug in the 2 for any of the x's. So the limit as x approaches 2 of x squared becomes 2 squared. Plus the limit as x approaches 2 of 2 times x is just going to become 2 times 2. Minus the limit as x approaches 2. Remember, if there's no variable up here, it's not like we can plug that 2 in anywhere. So here it's sort of meaningless no matter what. That's just going to be equal to 3. So 2 squared is 4, plus 2 times 2 is 4. minus 3, and then we get that equal to, well, 4 plus 4 is 8, minus 3 is 5. And it's exactly the same thing. Breaking this up into pieces was kind of pointless. You'll see, we can just plug that 2 right in from the get-go. 2 squared is 4, plus 2 times 2 is 4. Well, add those up, we get 8. 8 minus 3 is 5. Example 3 is an illustration of the following important result, which states that the limit of a polynomial function can always be evaluated by direct substitution. Just take that little number by your arrow, that number you're approaching, plug it in for x, evaluate it, and we get our output value. So the limit of a polynomial function. If p is a polynomial function and c is any real number, then the limit as x approaches that number c of p of x is just equal to p of c. Plug that c in, evaluate it for that value. And that's a good spot to end this video for time-wise. In the next video, we're going to talk about techniques to evaluate other types of limits.